In this video, we're going to learn about the law of conservation of energy. So firstly, we will learn about the actual law and what it says. Secondly, we will learn about different types of energies that exist. And thirdly and finally, we will walk through a step-by-step instruction on how to solve any energy conservation related problem. So this is more going to be of a conceptual video where we'll review through a really quick practice problem at the end, but it will be a very informative video that will teach you how to solve any energy conservation problem. So let's start firstly by examining what is the energy conservation law. The concept is the following: the total energy of an isolated system is conserved. Or in other words, the initial energy is equal to final energy. In other words, this is also said like this: energy is not created nor destroyed. Now, in our everyday language, right, we often say, for example, our energy is being produced, right, or energy is being wasted. For example, a coal power plant, right, produces electrical energy. However, that is not exactly true, because what a power plant does, it would burn coal, for example, so converting the energy of the heat into electricity, right? So energy is not created or produced, it's simply being transformed from one type of energy into another type of energy. We will work with this law a little bit more because on the next page, we're going to discuss how this law applies to our solving the problems. Now, but before we go through our step-by-step instruction how to solve energy questions, we should learn about different types of energies. Now, there are many different types of energies, but we'll only learn about 3 in this class. So first is the kinetic energy. So what I want us to keep in mind is 2 things when we learn about different types of energies. The formula, of course, to calculate the type of energy, and also the situation where it applies. So kinetic energy is the energy of the motion. The formula for it is the following: 1/2 times m times v squared, where m is the mass and v is the velocity of the object, right? So essentially, if a moving object, right, has some kind of energy, and we call that energy kinetic energy. Now, in order to find out if an object has kinetic energy, notice the formula, right? All the objects we're talking about have a mass. So therefore, really, if it has the velocity, it has kinetic energy. So in order to find out whether an object has kinetic energy, you need to ask yourself, does it have velocity? If it has velocity, it has kinetic energy. Let's take a look at the second type of energy. The second type of energy we'll learn about is the potential energy. It's the energy due to the height above the ground. So let's say, for example, I raise this pencil right above the ground. I give it some sort of energy, because if I let it go, it's going to start falling. This type of energy that objects have given its height above the ground, it's called potential energy. So the formula for potential energy is m times g times h, right? All of these variables should be very well familiar to us. M is the mass in kilograms, g is gravitational constant, 9.8 meters per second, and h is the height in meters, right? So the object will always have a mass, as we talked about. G is a constant, so in order for object to have potential energy, we need to ask ourselves, does it have height? All right. And finally, last type of energy we'll talk about is the elastic potential energy, or the spring energy. It has a very similar formula to kinetic energy. Of course, it will only be the spring energy will only be applicable if we have a spring and if that spring is compressed. Because what this X is essentially often written as delta X. So in this form, the formula for this is 1/2 k delta X squared. Delta X is by how much you stretch the spring. So is the final position of the spring minus the initial, right? Let's say you have, so it's by how much you stretch the spring from its equilibrium position, right? If you ever played with a string, right, the more you stretch the spring, the bigger the tension is going to be, the greater the energy that you just put into that spring. And K is essentially a spring constant, right? Different springs will have different stiffness. And essentially the spring constant is described, is in other words like stiffness of the spring. So it will either be given in a given problem, or you'll have to find out about it. The final type of energy would be thermal energy, which doesn't really have a formula, right? But if we're talking about energy being lost in the system, it's usually will be in the form of thermal energy. So, but we'll discuss that more in the next chapter. So for now, all I want you to focus are just those three types of energies, and knowing that if you have a velocity, you have kinetic energy. If the object has height, it has potential energy. And if it has a spring that is compressed, it has elastic energy, elastic potential energy. Any object can have either one of those energies or a few different types. So let's see how we're going to approach these energy conservation problems, right? So this is our step-by-step instruction. So the first, you always want to sketch the problem. This applies really to any physics problems. So since we're using energy conservation, so initial energy is equal to final energy, you need to define what is your initial moment and what is your final moment that you're talking about. So I'm going to, as I kind of walk through this method to make it clear, I'm going to essentially, well, let me go through this really quick. So again, you want to define initial and final moments. The second step, you want to ask at both initial and final moments, you want to ask those three questions. Does the object have velocity? If it does, it has kinetic energy, right? Does the object have height? Then if it does, it has potential energy. Let's say it also has potential energy. Is this spring that is compressed? Okay, let's say there is no spring that is being compressed, so it doesn't have elastic kinetic energy. Oh, there is, right? Rarely does it have all three. Usually the object will have either one or two types of energies at a given point. Then you do the same thing for the both initial and final moments, right? So you're asking, okay, at the final moment, right, is there kinetic energy? Is there potential, right? Is there height? Is there velocity, etc.? Then you plug in the equations for each type of energies. So 1/2 mv squared for kinetic energy and mgh for potential energy. And you plug in all the variables and solve for the unknown. So note, as I said before, at both initial and final moments, the system or our object can have one, two, or three types of energies, right? Although really it's rarely all three, it's usually one or two. So let's just solve a really quick practice problem to show you how this method applies to real world problems. So let's say, for example, you have a stone that is thrown with a velocity of 10 meters per second. So it's missing from the ground, right? From the ground. We need to find the maximum height that it reaches. So let's say it reaches the maximum height right here and goes down. So let's take a look. The first step is to identify the initial and final moment. So the initial moment will be when the stone is being thrown. The final moment is going to be, so let's say stone is thrown. The final moment is going to be when the stone is at its maximum height. Since, right, that's what it's asking about. So it makes sense to pick that point as a reference. So now let's ask at each of these points, let's ask ourselves those three questions. So at initial point, does it have velocity? Well, definitely, right? It's thrown with a given velocity, so it will have kinetic energy. Now, does it have height? So we'll assume that it's thrown from the ground. Therefore, at initial point, it does not have height. Therefore, it doesn't have potential energy. Of course, there is no spring, so therefore the only type of energy is the kinetic energy at initial point. What about at the final point? Does it have velocity? So if you remember back from kinematics, right, at this maximum height, the stone does not have velocity, right? Basically, when it goes top to the bottom, it stops for a second, for a brief moment over there at the top height. So it doesn't have velocity, right? Therefore, no kinetic energy. Question, does it have height? Well, definitely, right? It definitely has height, so it will have potential energy. And again, there is no spring that is being compressed, so therefore the only type of energy it has is potential. Okay, now let's write down our energy conservation formula, initial energy is equal to final energy. As we see, the initial energy, there's only kinetic energy. And the final energy, right, there's only potential energy. Now that we have figured it out, let's plug in our formulas for both. So kinetic energy has a formula 1/2 mv squared, and the potential is mg h. Now we can divide both sides by m, and v squared over 2 is equal to gh, and then divide both sides by g because we're solving for the maximum height. So 10 squared times 2 times, I will just use 10 for g for simplicity of calculations. So this will be 10 over 2 or 5 meters. Now, of course, this is a very simple problem, but it demonstrates our approach for solving these energy equations. So what I would recommend is that you would watch my other videos where I solve more advanced problems by applying this energy conservation method. But remember, if you don't know how to approach this problem, those are the steps that we outline in this video are how you should approach any energy conservation problem. So keep practicing and keep working on physics problems on your way to an A. Thank you guys. Right, or the displacement, so he starts here and ends here, so the displacement is in the upward direction, right? The displacement here is equal to 500 meters, and the force is equal to mg, or 20 times 9.8. Now, what about the angle between those two forces? So if the mg is down, and the displacement is up, the angle between these two is going to be 180. In other words, right, when you're climbing the hill, you have to overcome gravity. So gravity does negative work. It doesn't help you to move up the hill, right? It actually hinders you moving up the hill. So work will be equal to force times distance times cosine of 180. Once again, cosine of 180 will be -1. So again, mg does negative work here. So negative times f, right, is mg. So -20 times 9.8 times the distance. We get a final answer for work as 9,800 joules. Now, why did I include this problem? What does this problem demonstrate? What it demonstrates is that what matters, right, when we're talking about the work is the displacement. It doesn't matter what path the hiker took, or that the path was 30 degrees, right? The only thing that actually matters is how much, what was his final displacement. So his initial height and final height, where he ended up, right? That he ended up 500 meters away from his initial point, in other words, right? He could have taken any path, right? Work does not depend on the path that is taken. It only depends on the displacement. And you could be tested on this principle either through a problem like this one, or maybe on a multiple choice question. So I wanted to make sure that you understand this. In the next video, we're going to go over plots that have to do with work. Another very important concept that is going to be, I think, pretty quick and pretty simple, but is going to demonstrate another important subtype of work problems. Guys, keep practicing, and you can conquer physics, and keep working through these examples and watching these videos on your way to an A. Thank you.